Let us look at nature of standard sequence x to the power of 1 by n. This looks like this. X to the power of 1 by n is equal to x to the power of 1 by 2, x to the power of 1 by 3, and so on. So here x is a positive real number. So here we are talking of the nth root of a real number. So x cannot be negative to avoid getting into complex numbers. So what are the cases now? X would be 0, x equal to 1, x greater than 1, and x between 0 and 1. So let's take the cases one by one. X equal to 0. So 0 to the power of 1 by 1, 1 by 2, 1 by 3, and so on. This is nothing but a sequence of zeros. So this is a constant sequence, which means x to the power of 1 by n plus 1 is greater than or equal to x to the power of 1 by n. And 1 by x to the power of n plus 1 is less than or equal to x to the power of 1 by n. So by definition of monotonic sequences, and since terms are constant, it is convergent. So the limit as n goes to infinity of x to the power of 1 by n is equal to 0 when x equal to 0. Okay, now let's take the second case, x equal to 1. Very similar to this x equal to 0 case. So we have a sequence of ones. So again, this is a constant sequence, which means x to the power of 1 by n plus 1 is greater than or equal to x to the power of 1 by n, and 1 by x to the power of n plus 1 is less than or equal to x to the power of 1 by n. So by definition of monotonic sequences, and since terms are constant, it is convergent. So limit as n goes to infinity of x to the power of 1 by n is equal to 1. Pretty straightforward cases. So we have seen the case of x equal to 0, and we have seen the case of x equal to 1. Now let's look at x greater than 1. So for example, in this case, when x is greater than 1, it would be something like this. 3 by 2, 3 by 2 to the power of 1 by 2, 3 by 2 to the power of 1 by 3, and so on. So basically, nth root of a number greater than 1. So since x is greater than 1, x to the power of 1 by n is greater than or equal to 1. Let x to the power of 1 by n be equal to 1 plus p, where p is greater than or equal to 0. So we have x equal to 1 plus p to the power of n by taking nth power on both the sides. Now we have to figure out p goes to what number as n goes to infinity. So in the previous session, we have already seen. So we expand it using the binomial theorem. 1 plus p to the power of n is equal to 1 plus np plus p square times n minus 1 by 2, and so on. Now all the terms in the expansion are positive, since n is in the natural numbers and p is greater than or equal to 0. So removing terms from the expansion reduces the sum, making 1 plus p to the power of n greater than the truncated sum. So let us drop all the terms except first and third terms. Now, why specifically first and third terms? This we have discussed it in the previous session. So same reasoning also applies here. Keeping that statement in mind, we take up the first and the third term. We retain them, and rest all we ignore. So we have 1 plus p to the power of n is greater than 1 plus p square times n minus 1 by 2. Exchanging the left hand side and right hand side, the inequality change. So we have 1 plus p square times n minus 1 by 2 is less than 1 plus p to the power of Taking 1 to the other side, we end up with x minus 1 because 1 plus p to the power of n is equal to x. Simplifying it, n times n minus 1 goes down on this side and 2 goes up on the other side. So we end up with p square is less than 2 times x minus 1 by n times n minus 1. And taking the square root on both sides, we get p is less than square root of 2 times x minus 1 by n times n minus 1. Now, square root of 2 times x minus 1 by n times n minus 1 goes to 0 as n goes to infinity, which means as this square root goes to 0, as n goes to 0, what is happening? 0 is fixed because p is greater than or equal to 0. It can't go below 0. So from this side, this square root expression keeps getting or squeezing p to 0. So p gets squeezed to 0 as n goes to infinity from the positive side. So limit as n goes to infinity of p is equal to 0. Remember, we are not interested in p itself. We are interested in x to the power of 1 by n. What happens when n goes to infinity? So limit as n goes to infinity of x to the power of 1 by n is equal to limit as n goes to infinity of 1 plus p. So we are basically taking the limit on this statement. Using the algebra of limits, we can split this. We can have limit as n goes to infinity of 1 plus limit as n goes to infinity of p. Limit as n goes to infinity of 1, it's a constant. 1 is a constant, so it remains 1 plus limit as n goes to infinity of p. But that we have just now found that it is 0. So we have limit as n goes to infinity of x to the power of 1 by n is equal to 1. So we have seen the third case as well of x greater than 1. Now let us look at the last case when x is between 0 and 1. Just for understanding, 6 is since x is not equal to 0 and not equal to 1, but between them, x is a proper fraction. So for x in 0, 1 interval, x to the power of 1 by n is less than 1. So let y is equal to 1 by x. Y is greater than 1 because we have taken the reciprocal of a proper fraction. It is going to be greater than 1. Now let y to the power of 1 by n be equal to 1 plus p, where p is greater than or equal to 0. See here, y is greater than 1. So we are just saying let its nth root be 1 plus whatever be the small quantity that it is greater by, that is p. So taking the nth power on both sides, we get y is equal to 1 plus p to the power of n, and the remaining steps are exactly the same as in the previous case of x greater than 1. What we end up with is limit as n goes to infinity of y to the power of 1 by n is equal to 1. So since x is equal to 1 by y, implies x to the power of 1 by n is equal to 1 by y to the power of 1 by n. And x equal to 1 by y we got from this by rearranging x and y. Taking the limit as n goes to infinity of x to the power of 1 by n is equal to limit as n goes to infinity of 1 by y to the power of 1 by n. So which means limit as n goes to infinity of x to the power of 1 by n is equal to 1. So the fourth case also addressed. To summarize, we have for the sequence x to the power of 1 by n, x equal to 0 implies limit is 0. When x equal to 1, limit is 1. When x is greater than 1, limit is 1. And when x is between 0 and 1, the limit is 1. Or we can write it in this form. Limit as n goes to infinity of x to the power of 1 by n is equal to 0 when x equal to 0 and 1 when x is greater than 0. That was the nature of standard sequence x to the power of 1 by n. Now, if you found this session helpful, please do like, share, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.